Good evening, everyone. We are in the week 9 problem solving session of the course, Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. Week 9 is about digital control implementation using microcontrollers. I am Tejagolla, a third-year research scholar working under Dr. Santanu Kapat at IIT Kharagpur. Let me share my screen. Can you see my screen?
Yes.
Okay.
Yes, sir.
Okay. So we are in the week 9. So week 9 is about digital control implementation using microcontrollers. So previously, until last week, we have discussed Verilog implementation and FPGA-based implementation of the digital control that we have discussed. So previously, we have discussed about digital control architectures, simulations, validation, different models to design controller, and then ADC, DAC, and then we have learned Verilog, and then we have seen Verilog implementation. But this week is about microcontrollers. So we'll not be implementing digital control in microcontrollers, but this is just like an introduction to microcontrollers. So whatever like the controllers that we have learned, they can still be implemented using microcontrollers, but we'll just give a brief introduction about microcontrollers, mainly STM as well as Texas Instruments microcontrollers, and we'll see their applications as they're already been used for quite a number of years, and we'll look into it. So before we go into the week 9, let me just summarize what we have discussed in week 8. So week 8, we have discussed about digital controller implementation using fixed point arithmetic and Verilog HDL. So like we have discussed few digital controller implementations. So first thing is voltage mode control, digital, fully digital, because there is only one loop and it is also in digital. And the second one is the mixed signal current mode control. One loop is in digital voltage loop and current loop is in analog. So this is mixed signal. And then we have also discussed about the digital PSM. So I can say digital voltage mode control and digital. And then we have discussed a few problems. So if you go into the summary, we have the digital voltage mode control. And here it is again mixed signal, two loops. Again, here it is digital pulse skipping modulation. So first we have in all these three, first we have discussed about the top-down design methodology. So we have seen the architecture, and then we have discussed about how to implement it using Verilog HDL, as well as some hardware results. Here also we have seen the top-down design methodology, and then Verilog HDL implementation and hardware results. Here also it is the same thing. So if we consider digital voltage mode control, you are able to hear me, right?
Yes, sir.
So in digital voltage mode control, there are say few sub-blocks. One is the main function. So main function, all of the control techniques have main functions, but it has sub-blocks. So we have here clock generator, and then we have digital PID, and then we have DPWM with Deadtime. And then in mixed signal current mode control also, we have the main block, and then we had clock generator, and then we have digital PI because it is current mode control. So we had not discussed this because they are same as this. This we have discussed. So that's why this we have not discussed last week, but it is still the same thing. And then if we come to the important point, which is the current reference, we have discussed what is current reference, why it is needed, and what is the main purpose of it, and what is the working of it, and how to write in Verilog HDL. And then the last one is again the DPWM, or you can say gate pulse generation. So it is also DPWM with the Deadtime, or pulse generation with Deadtime. Now, in this digital pulse skipping modulation, again we have clock generator, and then we have that PSM logic block. Inside PSM, we have the PWM generation, because we have to generate the open loop duty cycle. So we have here open loop duty cycle, because the duty cycle is fixed, and depending upon the closed loop, whether it will be charge pulse or skip pulse. So who is deciding whether it is charge pulse or skip pulse? That is being decided by the PSM logic. So this duty ratio is always fixed by the user. So this open loop duty cycle is fixed, but this will decide whether it is charge pulse or skip pulse. So depending upon this logic, it is being generated. And in all of these cases, we have seen hardware results, and we have seen the load transient as well as reference transient results. And in digital pulse skipping modulation, we have seen some crucial results as well. And then we have discussed the few problems based on whatever we have discussed in the last week. Now coming to week 9. So as I have discussed, this is all about microcontrollers. So we will be discussing microcontrollers, some overview and what type of microcontrollers are available, how to select microcontrollers, and what applications can be targeted using these microcontrollers, and what are the commercial products that are available. All these things we'll see. So there are two different companies that like one or two of many such companies that are making microcontrollers, and one is the ST microcontrollers, which are actually famous, both these two companies. One is the ST microcontrollers, and then the Texas Instrument, or maybe I'll say ST Microelectronics. So we have ST Microelectronics, and then we have Texas Instruments. So these are the like two big giants in microcontroller industry, and their products are highly popular. So we'll be discussing about these two, and here we discuss about STM32 board, and here we'll discuss about C2000 board. So first we'll start with this, and then we'll go into the Texas Instruments board. So the outline is as shown. So first we have STM32 as so if I say STM32 is a overall family of one type of microcontrollers, and this is one of that family. So this is one such board, G4X. So it is a part of this family. So STM32 comprises of different microcontrollers, and STM is one such microcontroller. So why did we choose this? Why only this? So that we'll be discussing in the slides. And first we'll discuss about the overview, and then we'll discuss about selection for digital SMPS. So digital D-SMPS means digital switch mode power supply. Let me bring this video down here. So this is digital switch mode power supply. So for digital switch mode power supply, how to choose the microcontroller, that we'll discuss, and what are the software tool requirements. And then I'll show a live demonstration of GPIO toggling, which has already been discussed, but we can again discuss it, and I can show if you have any doubts, we can have a good discussion. And then ST Microelectronics people have shown LLC Converter Realization. Ranjay Malik sir has shown LLC Converter Realization, lecture number 84 and 85. So he has discussed about power plant, and then modulator design and feedback management, and what are the protections that they consider in LLC. And then sir has shown their product, also some hardware results. We can quickly see how this microcontroller is changing the implementation of digital control in ST Microelectronics, and what type of products of theirs contains this ST microcontroller, and what is the advantage, and what differences that this controller is making. Then coming to C2000 microcontroller, which is of Texas Instruments. So again, we'll see some overview and then what are the software tools requirements and why C2000 microcontroller is used and what are the benefits that it offers. And like we'll dive into the specifications of this microcontroller. And then at the end, we'll solve a few problems. So this week is mainly about some introduction for you to know about the microcontrollers, what type of microcontrollers are available, what are their specifications. So all these benefits and where they are using in the real life products and what differences they are making, what are the advantages or benefits they got by using this microcontroller. So you are free to choose any microcontroller based on your comfort and convenience. So we'll start with STM32. So STM32 is of ST Microelectronics. So this is ST Microelectronics. And 32 is because it is a 32-bit microcontroller. So we'll discuss about its overview as well as digital switch mode power supply. So this is digital switch mode power supply. So we'll discuss about STM32 and then we'll discuss about this STM32G4X, why we have selected. So first, if we talk about STM32 overview, so as I have mentioned, it is a 32-bit microcontroller IC from ST Microelectronics, and it is based on ARM Cortex-M processor. And if you categorize STM32 family, it basically is classified into 4 categories. So what are those 4 categories? These are the 4 categories. The first one is the mainstream MCU. So it is addressed, like it addresses a broad range of application, and the other one is the high performance MCU. So it has high efficiency as well as high integration, and it is best in class system performance. And the other one is ultra low power MCU. So as we are talking about ultra low power, so we talk about energy efficient, and depending upon their applications, this are used. And the fourth one is the wireless MCU. So for wireless connectivity, they have microcontroller. So this is used in wireless connectivity. So why do they have so many different categories? So each of them are optimized for that particular application. So they are not making a MCU for a generalized application. So they are making it specific for different applications. So it will be like efficient as well as optimized for that application, and it will have the hardware and other features related to that application so that it will be beneficial for that particular application. And similarly, they have microcontrollers for various applications. So now if we talk about analog switch mode power supply as well as digital switch mode power supply. And digital switch mode power supply means basically the controller that we are considering for this power supply is digital. So if you consider analog power supply or analog controller, what happens is everything is like in the hardware. So if we talk about, say, we are implementing PID controller, how do we realize this? We realize PID controller with op-amp and plus some resistors, comma capacitors. So this will decide the KPKI KD values. Now, what if I want to change KPKI KD? Then I have to manually check what are the resistor values that will result in this KPKI KD and what are the new values. And as you know, we do not have like infinite resolution resistors. So we have to find the nearby resistance value. Say if you got some X ohm, so whether that X ohm is actually available, you have to see, or if it is not available, then you have to adjust with the nearby resistor or so. It cannot be exactly that particular resistor value till decimal point. So we'll get nearby KPKI values. Also, we have to mount this RC values on the board. So it will take some size, and depending upon the other architecture that you have put, protection circuit, everything, depending upon that, the size will increase, and there is no flexibility as such, because it becomes difficult for us to, every time if I want to change KP, every time I have to see what are the resistor capacitor values. I have to select that particular resistor capacitor value, and then I have to mount it and then test. Also, this is the V reference. So if there is no such provision provided for V reference to change, then it would be difficult to change that V reference. Also, here everything is in hardware, so there might be limitation due to hardware. There might be limitation due to hardware, and it becomes difficult to manually change it every time. All those things and all these constraints are there. Whereas coming to digital controller, we have set of instructions that we are writing in whatever software that they are recommending us, and then accordingly it is changing. Say digital PID. So the digital KPK KD values, as we have seen in Verilog as well, we are giving, we are setting the resolution, right? Say Q1.9 or Q2.8. So depending upon our resolution, we choose this QM.N format. And if you see, we have this much resolution in the gain. So we have the flexibility of choosing KPK KD. And say if I have chosen KP equal to 5, and now I want to choose KP equal to 4. What will I do? I'll change the value. I'll run the Verilog code and it will be implemented. I don't have to change any R value, C value, or mount anything differently. I only have to change in my code and then again run it and burn the code into FPGA, and now it will become KP equal to 4. So all these flexibilities are there. So the first advantage we can say is the flexibility and less size. So we can, so the microcontroller size is fixed no matter how many lines of code we write or what many protections we can put. So the size will be same here depending upon the architecture or the hardware that we have considered. The size might increase, and also no much flexibility available. Also here we can write very high complex algorithms in the code, because we are basically writing in the code, so we can write very high complex algorithms in the code. Whereas here everything should be realized in hardware, and not much flexibility is there. And also KPKKD resistance values might not be exactly same, so there might be some tolerance issue, and all these issues will come. And here we have immunity to noise and more flexibility, all those things we have. So that's why, and microcontroller and FPGA, like they are also the same. They both have their own benefits, and both are almost same, except microcontroller has some other benefits, and depending upon the application and your requirement, user requirement, one can either select microcontroller or one can select FPGA. So there are wide range of FPGAs available in the market. Also, there are wide range of microcontrollers available both in ST Microelectronics as well as Texas Instruments. So one has to select that particular microcontroller which better suits for that user's particular application, and then accordingly he has to download the softwares and write the code, run the code, and check whether the hardware is working or not. Also here they have provided some protections in the code itself. Here say if you want to provide any protection, it has to be a hardware. So in ST Microelectronics, they have written some lines of code like completely it might not be hardware, but minimal hardware plus software firmware. They are providing the protection circuit as well as high complex algorithms inside the code. So it makes their life easier, compact, and more efficient, also more flexible. So that's why people are going into digital controller, and it will be like mixed signal also, not fully digital in the case of current mode control. So, but they're getting the advantages of the digitization, the flexibility, all those things. So these pictures are taken from the ST Microelectronics. These are the same as what have been discussed in the lectures also. So now if we think about STM32 for digital switch mode power supply. So these are the 4 different families that we have discussed earlier. So first one is the mainstream, high performance, ultra low power, and wireless. So those are these 4 families. If we talk about, so this is one family, and this is the other family, and this is the ultra low power, and this is the wireless. So for wireless, they have 2 such ST micro electronics microcontroller boards, and for ultra low power, they have so many wide range of microcontroller. So only the last 2 names are changing. So it is L0, and this is L1, L5. This is L4 and L4 plus. So depending upon their microcontroller, their frequency might change, the benefits they offer might change. So you have to go to their datasheet as well as application note and see what that microcontroller offers. And here high performance, we have F2 as well as F7, F4, H7, and they offer here it has two such cores. Here they are single core, and if you consider these two, here you can see blue dots, so which means they are for mixed signal applications. So these are for mixed signal applications, and these are optimized for that. So whatever hardware like ADC, DACs, comparators that we will be using, so they'll put that inside the microcontroller. So for mixed signal applications, these are necessary, and they are available in plenty of number in the microcontroller itself. So for these applications, whatever architecture or whatever additional hardware that we might be needing, that is already available. So we don't have to bother
And
about.
what does this dot
So
represent?
yes, so these dot means that they have some meaning, and this dot they'll explain in the bottom. So this is the blue dot, and here they have this dot, which means it has this Cortex M0 radio coprocessor. So they want to say this dot means it is optimized for mixed signal applications. So these two are basically optimized for mixed signal applications, which whatever we are discussing, all this course is about. So if you see here, it is 72 megahertz and this is 170 megahertz. So depending upon your clock frequency, you can choose any one of them. But in this course, we are talking about STM32G4. STM32 G4 family, and it has 170 megahertz clock, main clock. In the FPGA, we had 100 megahertz. Here they have 170 megahertz clock, and we'll see. So, like, this is the reason why we chose this microcontroller, because it is optimized for mixed signal applications. So it is optimized for whatever concepts that we are discussing, and out of these two, it has higher frequency, which means better resolution. So that's why we had selected this microcontroller, and now we'll discuss about this microcontroller in detail. So this is the STM32 G4X. So this is the STM company name, and this is 32-bit, and this is the family. G4X is family, and it is of which one? Mainstream microcontroller. So this is the mainstream microcontroller, and it is optimized for mixed signal applications. Okay. Now we'll go into the overview of this microcontroller. So as we can see, it has many like specifications or many things that are already coming with this microcontroller itself. So if we talk about first one is the high performance ARM Cortex, the MCU IC with 170 megahertz, which is sufficient for our applications, as FPGA has 100 megahertz. So this is almost 1.7 times of the clock that we have. And they also have 3 accelerators, ART, routine booster, whatever application that they serve. Or if you want to know, we have to go through the data sheet. So whatever these mean, then we have to go into the data sheet and we have to see what they mean. And it has 7 comparators. So in our mixed signal, we are comparing with the inductor current with reference, right? As you remember. So in the mixed signal, we have plus minus. This is IL and this is I reference. And how this I reference is coming? This I reference is coming from a DAC, right? We have DAC and the input is I reference N. So for mixed signal current mode control, we need one comparator. So it has comparators, and we also need DAC. So it also has DAC. So in the case of FPGA, when we were discussing, we had discussed about signal conditioning board. So you need a specific signal conditioning board which contains ADC, DAC, comparator, other circuitry. Whereas in the case of microcontroller, they come by default in this particular, because this is made for mixed signal applications. So they have these comparators. Whether these are available in other microcontrollers, that we have to check, because it is optimized for these applications. So they have provided comparators, ADCs, and DACs inside this controller itself as this is used for the mixed signal applications. So we have 7 comparators, 5 ADCs. So again, you have to see what type of ADC they are using. So I think they are using SAR ADC. So again, it has some delay. So you have to go into the datasheet and see what is the delay, how much delay it will generate. So at what frequency I have to operate the ADC at, and all these things you have to see. So it is again 12-bit ADC. So they have 5 12-bit
I have
ADC.
a doubt.
Yes.
Sir, which is faster, sir? FPGA is quicker in cap computations or microcontroller is
That
quicker in
depends upon
computation?
the frequency, right? So now this is operating at 170 megahertz, and
Okay.
FPGA, it might have 100 megahertz, or some FPGAs are even more, like 5 up to 500 megahertz they have. And here the ADC
If
is
the
SAR ADC. Yes.
if the clock frequency is same in both, then which compute faster?
Then again, now it like if the clock frequency is same, then both of them almost have same performance.
Okay, like sir, the main thing that is confusing me is in our organization, for some projects they are using FPGA,
Yes.
and for power electronics applications specifically they are using microcontrollers. What might be the difference?
Yes, so like one such thing is, see, whatever application or whatever product that we are going to make, first thing is the cost, and the second thing is the size. So depending upon their cost and size requirements, or you can say speed as well as performance. So first thing is cost. Microcontrollers are a bit like less cost compared to FPGAs. FPGAs are a bit costly, and size also it matters. So what is the size of the microcontroller that you get, and what is the size of the FPGA that you are having, and also depending upon the speed and other factors, depending upon the application, they select the FPGA or microcontroller. So in our lab also, some people are using ST microelectronics for high power, like LLC and PFC, and some people, including me, we use FPGA. And when I use FPGA, all these comparators, ADCs, DACs are separated. So, but in the case of microcontroller, they are already inbuilt, so you don't have to have separate signal conditioning code. So depending upon the application, either you can go microcontroller or FPGA. So it is the user choice whether you want to go to FPGA or microcontroller. With both, you can implement the same controller. See, when I design, say, for a buck converter, say voltage mode controller I have designed. My say based on small signal, I have a requirement on bandwidth, I have a requirement on phase matching. Either of these can be achieved either using FPGA or microcontroller, but it is up to you which one you want to select. And there might be some like you have to see in deep. Say the FPGA that we are using, it has a pipeline ADC, so it has lesser delay compared to SAR ADC because it is serial and pipeline is parallel ADC. So the delay will have effect, and you have to see what is the speed of DAC that they can go, because we are specifically selecting a ADC and then we are making a board for ADC. So it is again up to the user choice. If you want to implement directly without making signal conditioning board, then you can go for STM32 or C2000 Texas Instruments, and then you can take advantage of the hardware that is available, that is already there in the microcontroller, and then you can use these ADC stacks. They also have many codes, example codes that are available, so you can refer to those codes. Or if you are comfortable with Verilog and if you want to work on FPGA, then you can do that. It is not that you have to do this or do that. It is again to the application, mainly the cost, size, speed. If microcontroller is somewhat lesser cost, and if your application that it cannot afford that much cost like of an FPGA, then you can implement in microcontroller as well. So. And it also has some safety robustness. It can be operated with USB or Type C. So all these advantages that we can find in the microcontroller. So like this is an overview of the microcontroller. So what it has. So let
So,
me, yeah, hello.
sir, can I say like microcontroller is an ASIC?
Microcontroller.
is
Hello.
an ASIC, application specific IC.
Yes, I see. Yes.
Okay, whereas FPGA is not.
No, FPGA is also we are programming it, so we cannot actually say it as ASIC. ASIC is a specific for particular application. So, but microcontroller we are able to reprogram it. So we cannot actually
Okay,
say it also has programmability. So, like if you say DAC, we
o-
can say it is an ASIC because it is specifically for DAC.
okay, okay, sir. Okay.
So like I'll go into the details. So it has that IC which internally they have the architecture. So using the software hardware interface, we can program it and accordingly change. So inside this IC they have these small ICs that they have made, not IC, small architectures inside this big IC. Okay, so like they have let me zoom in. You can see the zoom in screen, right? Hello. Hello.
Able to see.
Okay. So like they have different JTAG connectors on this side, and here they have serial peripheral interface SPI, and here they have DACs. So 4 DACs are here, and each DAC has different channels. And here they have SRAM, and here they have SAR ADC, as I have discussed. They have SAR ADC here, so they have 5 SAR ADC and input to microcontroller interface. And here GPIO, which is general purpose input output ports. So they have few ports here, and then timers. They have timers which will be used to generate or used for DPWM or other purposes. And here they have USART communication, SPI communication. So they have a different set of communications available. UART, USART, SPI, CAN bus protocol, as well as USB, and then SPI. So they have different communication protocols, and ADCs and DACs are already available. So there is some debugging software also, and they have ADCs, GPIOs, and then high resolution timers for DPWM. And in these timers also, they have some advanced timers which offer some other extra benefits which you can find in the datasheet. And serial peripheral interface, then comparators, op-amps, which are needed for our current mode control, mixed signal current mode control. And then DACs, they have available, which is also mixed signal current mode control. It is available. They have this power input here. So this is the input to the microcontroller. So microcontroller needs input. So this and clock we have 170 megahertz. And these are all communications, different type of communications that you can use to communicate with the other device, and you can use any one of them. And, we are not going into the details. These details are, again, you have to go through the datasheet, how to write the code, how to access them, how to initialize them, what are the instructions. As you know, each different microcontroller have different type of syntax, but the overall the working principle remains same, but you have to use that particular instruction syntax, and you have to access that particular register, and then you can write the code accordingly. We'll not going into the coding part in detail, but we'll see what type of softwares that we can use. Just a minute. Okay, there are 3 more minutes. Okay. So, hello.
Sir,
Yeah.
there is a specification called high resolution timer, right?
Yes.
That is a.
So
sir,
these
in that,
resolution, yeah.
tell me, sir. I just, what
No,
does
no,
it
you
mean?
continue.
Because,
Sorry for interrupting.
sir, this is the, does this term represents more number of frequencies
Yes,
within
yes.
a
So
band?
high resolution type. Yeah. So when we say counter
Okay.
in FPGA, say FPGA, we are using 100 megahertz. So it has 10 nanosecond, right? But in the FPGA, they are using specific high resolution timer, not all timers, some timers. So like in this say microcontroller, I can say, I'm not exactly sure, but it is a few hundreds of picoseconds. Few hundreds of picoseconds is the resolution. So it can be that much, like resolution can be that much small. So Here we have resolution 10 nanoseconds. Again, it changes from microcontroller to microcontroller. I'm not sure. I think it is less than 200 picoseconds, 170 or something resolution. So if you use that particular timer and if you need that much resolution, you can still use. So like this microcontroller is optimized for mixed signal. So they are providing these timers, and again advanced timers. You have to check what are the benefits, what are the differences between these two in the data sheet.
So this is mean, does it mean that microcontroller is somewhat have less quantization error than with FPGA?
Yes, yes. So it all depends upon the clock, right? So here we have 170 megahertz clock, which means by default it has resolution lesser, and they might be using some different architecture to reduce that resolution. They might be scaling up the clock, and whatever they are doing their algorithm inside, the output is that we are having, or we are getting lesser resolution, like high resolution, not less resolution, high resolution and less. Yeah, so all these details are available in the ST Microelectronics website. You have to go to that website and you have to see what are the, like, all these things are also available in the datasheet. So you have to go each and individually thing if you are interested, but it is not mandatory. But these are all the things that come up with this microcontroller, and you can find this on their website or datasheet also. There is less than a minute. If this meeting ends, kindly join so that we can have a discussion. So STM, we have this STM32 microcontroller. So how to use or how to write the code. So there are some softwares that ST provides, which are also free. You can download it from the STM website, and this has also been discussed by Akshat sir in the video, so I'm not going in details of how to download, but we'll be using this STM CubeMX software today. I'll show to write the code, and then for compilation and debug, they have different partners like ID, IAR, Kyle, but today we'll be using IAR as they have shown IAR. We'll use this IAR system, IAR embedded. So this is one such software, STM CubeMX32, which is free, and installation has been mentioned. The procedure has been mentioned in the lecture video, so I'm not going into the details. So this is also IAR webbench, which is also again free. So we can use this, and this is another programming tool which has not been discussed, and for implementing it is not needed. So these two softwares are needed for implementing any algorithm. So we'll discuss these two softwares in details. I'll show one LED blinking example that has already been discussed in the session, online session. So these are all the softwares. One is the STM32 CubeMX, the other one is IAR Webbench. Other software also available. You are free to choose any software, but we'll discuss this software. The other one is the hardware solution. So they have so many hardware solution. One is the STM32 Nucleo board, which we are using. So we are using the 64-pin this STM32 G4 board, Nucleo board. So I'll show these details in the upcoming slide. So we are using a board which looks similar to this. And so they have different G4 series. So we will be using this series or this board. I'll show the board in the upcoming slides. And then they also have evaluation boards, which you can use to test the working of their whatever boards that they have made. And so they have these evaluation boards, and then they have this motor control pack, which is made for this motor things, and this is fully featured for motor control. So they have made it for specific purpose only, and for motor control applications, you can select this board and you can do this. So for different applications, they are making different boards. And if you see here, this is made for some application, and they are mounted the MOSFETs, necessary number of MOSFETs and gate drivers on the controller board itself. So you can use these MOSFETs and you can use the controller as well. So these are the discovery kits. So they are again application specific. So they might have done for specific application where you might be needing these MOSFETs. and they have made it for that. So they have optimized it for that particular application, and they are also providing the MOSFETs. So now majority of the hardware comes in this single board. Whatever power stage that you have, you just have to connect this with the power stage. Not only it reduces the size of the overall hardware, but also it is optimized for that particular application, and they might also be giving several features or benefits for that application, which is already coming as a package. And today we are discussing about this board with this name. So as I'm mentioning, the name of this board is STM Nucleo G474RE, 32-bit, and for mainly made for mixed signal application. And in this family, it is G474RE, the name of the board. As we can see, the name of the board is here. So here you connect the micro USB, which again USB micro USB wire you can connect to your laptop, and then you can dump the code using this. And this is the MCU, the debugger ARM Cortex, and this is the microcontroller, which has all the ADCs, comparators, everything inside. And these are the pins, extra pins, GPIO pins, which you can use for any PWM generation or other signal generation, high side signal, low side signal, or if you want to give low transient, we need to give a pulse, so difference tangent. So all these external pins we can use. And it also has Arduino connectors, and different LEDs, say LED 1, they have LED 2, they have LED 3, they have. So accordingly, we can write the code for that particular LEDs, and we can test our code. And similarly, this is the backside of the microcontroller board. So this is the board that we are going to use today, and we'll discuss about how to write the code and everything. So before we go into the GPIO toggling, I would like to show you the board. Maybe I'll stop sharing my screen, and maybe I can show you the board. So let me video. I have to remove the background. So you can see my video, right? Hello. Hello. Hello.
Yes, yes.
Yeah. Okay. So like this is the board that we have just discussed. So this is that micro USB which will be connecting to the USB, and this is the debugger IC, and this is the HDMI which has all the ADC stacks, everything inside. And here they have one button, user button, so which you can use to like give interrupt, or you have to write the code accordingly. So push button. So and this is one reset button, and they have this general purpose input output pins on both the sides, as well as other LEDs as we have discussed previously. So you can access any of the LEDs and all the DACs, comparators, everything inside. So we have to feed the analog input, and we can digitize it using our code, and then we can put PID control, PI control, whatever, and then we can directly give PWM signals, and these PWM signals we can directly give it to our power switch. So now I would like to show you the working of the board using the softwares that they have mentioned. So first I will show you the interface of the software, then I will show you the working of the code. So let me share my screen. You can see my screen, right? Hello.
Yes.
Okay. So like this has already been discussed. So like we have to first open this software STM Cube MX, and then we have to get this LED project or GPIO toggle project. And then we have to open this IAR software, as we have mentioned, IAR embedded workbench for ARM processor. And then we'll check the main functions, and then we'll program it and run it. So first I'm opening that STM32 CubeMX software, which I have installed. And the installation procedure is mentioned in the videos. You can also go to STM website and you can directly download it from there, which is again a free software. So let it open and so the software has opened. So this is the interface. So you have to log in so that it will know that you are the user, and here we have file if you want to start any new project or load project, and then we have different inputs, and here is the update. If there are any update, you can click it and accordingly it will update to the new model. And if you want any package, you can install the package. Say we are using STMG4, right? So STMG4 I have two and I have installed both of them. And if I want these packages, then I can install these packages as well. But I have installed the latest software. Say if I'm using STMG0, then I have to install the software accordingly. I'll click it and then I'll install it and it will automatically install. And here, these are the softwares that I have recently opened. So if I want to access any example project that are that came with this software, so when you install this, all the projects, example projects will be stored in a folder in your laptop. So you can access them or you can access from here itself. So I can show how to access them from here. Also, I will show how to access them from the folder. So let it open. So this is that interface. Now we have to select. So either we can select by using any of these such things, vendors, what are the boards, what is the MCU, all these things. Either you can use this or you can directly search. So I know the board name. So it is STM32 G4.
You are selecting from the third from examples, right?
Yeah, sorry.
Like, could you please repeat the previous process one?
Okay, so we are selecting the example. And I am selecting the board STM32G4. STM32G4. So now I will select STM32G4. So whatever examples that ST is directly providing, the already examples are there. They have written the code. Only we just have to access which one we want to know. So they have ADC as well as comparator, Cordic, and all these things. Say I want general purpose input output. So I have to go EFG. So GPIO toggling. So GPIO input output toggling. So accordingly, I'll see which board. So mine is Nucleo G474RE, right? So they have code for different. So I'll click on this. It will take some time. So it is asking for some installation and it will open it.
Sir, from this is how I can start my project from example, right?
So yeah, these are the example projects that are already available. We are not starting any project.
Okay.
These
You
are
have,
already.
yes, you entered the third one, right? You
Yes,
click the
yes.
third
So
one.
I have entered the third one. So access to example selector. So whatever examples that are available for different families of ST microelectronics, I have selected the STMG4 family, and from there I am getting this GPIO toggle example that is already there. So after here, these are the pinout view, and you can configure the clock, but they have already configured. So everything they have done, I have not done anything. I am just accessing what is there. Like different examples are there, out of which I have selected this one, which has been shown in the lecture videos, and I would like to discuss this. So I have opened this now. So this is the interface where you can access any pin. Say if I want to access this pin, so I can use this pin as any one of these. I can either use it as SPI to SPI for SPI protocol or I2S, or it can be used for ADC pin. So accordingly, you have to configure the pin, and when configuration is done, then you click generate code. Now I am not configuring because they have already done in the example and I need not configure. But if I'm starting it from afresh, then I have to configure all the pins. So Now it will say either you open the folder or you open the project. I'll directly open the project, or you can open folder also. From the project folder, you can again access it. So now when I say open project, it goes into IAR embedded workbench. So now it has initialized everything. So it has this int main function similar to C. Then it has HAL initialization and the system clock, main clock initialization, and LED2 we are accessing. So LED2 and the GPIO, all the initialization it has been done. So this is the while loop, forever loop, while one. So it says HAL GPIO toggle pin. So we are accessing LED2 GPIO port and LED2 pin. And this is the HAL delay. Now what I have to do is I have to first download and debug. So I'll click this, but I have to connect the microcontroller. Let us see. My microcontroller is not connected, so let me connect.
Sir,
Yeah.
sir, if I haven't downloaded IAR and I have downloaded only like STM32
Then you cannot do.
MX only.
You can do.
Oh,
You
okay.
need both
If
now.
both are installed, like if I directly open the project, IAR will be open, right?
Yes, yes, that I'll show. So I have not connected my microcontroller, so that's why it is saying that failed to search for the probes. So I'll again click on this. Let it run, and when it runs, we have to click go. So when I click go, my LED will blink and it is blinking, but I will show the blinking of the LED like when I turn on the video. So this is one way. So we are accessing the example directly, and we just run and we are checking whether it is working or not. So now I am closing this. Also, I am closing this because from the third option, I have accessed the example project and I have opened. The other way is I can, I'll show. So in this users repository in Dell STM32 cube folder, they have repository. So we'll let us go there. So this is the STM cube. So inside this users STM cube, we have repository, and then latest version. Anything is fine. I'm going to the latest version, and then I'll go to the projects. And in projects, they have G4 multiple boards. We are using 474 RE. I'm going into 474 RE. So templates, examples, all they have. So I'm going into examples. So in examples, they have so many examples. I want GPIO, and GPIO, I want GPIO toggle. In GPIO toggle, so this is the STM 32 cube MX software, or you can go to EVA, and this is the IAR workspace. So I can directly click IAR workspace. And this is again the same code. So int main, HAL initialization, clock configuration, and then while loop with 1000. So it is 100 millisecond previously. I can make 1000 or I can make 100. So accordingly, the code will work. So this is the example project. So if I want ADC, then offset compensation, gain compensation. Accordingly, I have to see what that example does, and I have to cross check whether it is doing it or not. So let me go back to my codes. So this is the LED code, EVA. So it is just the copy paste of the code I have implemented here as well. So now I'll turn off the screen and I will show how that LED is working. Will stop sharing, and now my video is visible. I'll unblur, and so first I'll run my code. So first, you remember that 1000, right? So 1000 means it is 1000 millisecond, which means 1 second. So it happens like toggling happens at the rate of 1 second. So now I'm running the code, and I'll show you. So this is the LED that is blinking. So it is on for 1 second, off for 1 second. So this is the LED2. You can see, right? Hello.
Able to see.
Yes. Okay. So now what I'll do, I'll increase the speed. So that 1000 number that we had discussed, now I'm making it 100, which means 100 milliseconds. So it will run at a rate of 10 times faster than what it is already doing. So I'm first running the code and then loading the code, and I'll run it. So it is loading. Now I'll click go. So now if you can see, it is operating at a much faster rate, right? So I have just changed the delay. So microcontroller, those people have directly provided that HAL delay function itself, so that I have to just insert the name. Whereas in the case of Verilog, you have to write the code so that the delay will be coming. So now what I'll do, I'll increase the delay to say 2000 or say 2000. And then again, I'll click run. Now it becomes 20 times slow, because now it is 100 and I'm making 2000. So let it run. And I click go. So now it is 2 seconds. So it is 2 seconds off, 2 seconds off, 2 seconds off, 2 seconds off. So accordingly, you can write the code and change accordingly. So this is one way where we are accessing the codes that are already available. So there is another way for which, let me share my screen. So for which you have to go to STM32. So this is the first way that I wanted to discuss, where the codes we are accessing, and so we have seen that these three are there in the main function. Okay, I have to connect my pad as well. You can see my screen, right? Hello.
Possible.
Okay. So this we have seen in the main function. Now what I'll do is, what if I have to do the code all from the scratch? So then this is the procedure that they have discussed. I have written in terms of lines, so you can map one to one. And as this will be uploaded, you can also refer. So first it says open STM_Cubex, and then you have to click select access to MCU selector. So where is my software? So this is my software. And this is the first option, you can see, right? Access to MCU selector. I'll select access to MCU selector. And then I have to select STM32 G474 RET6. So let it open. Again, these details are not necessarily needed for you to learn. I'm just showing so that you'll be interested. So mine is STM32 G474 RET6. So I have selected this, and as you can see here, it came. So I'll double click on this, and it will create the new project automatically. Now I'll go back to the procedure. The procedure says you have to configure PAI5 to GPIO output. So now the question is, why this PA5 came into picture? What is this PA5? We'll discuss. So why PA5? So let me go
I
back.
have doubt,
Yes.
sir.
Hello.
I don't have access to this board, right? Like,
Yes.
can I just program and
No, you
whether I
need,
am able to?
no, you need the board to test. Otherwise, you cannot load the board. It will throw that error that USB drivers are not installed properly.
Sir, in case of C2000, like TCS Code Composer Studio, like there is an access to watch window, right? Where at least the counts at least will be visible. From that we can debug.
Sorry, can you ask the question again?
In Code Composer Studio, there is
Uh-huh.
access to like watch window, right?
Yes. You're talking
In
about
that watch
C2000.
window, yes sir, yes sir.
Okay.
if we like we compose it in like Code Composer Studio, like for programming, there is an access to watch window
Yes.
in the software.
Yes.
There, if I'm right, like we are toggling the LED for that specific time, there will be specific counts, right?
Yes.
That will be visible. From that, we can debug if even we don't have access to that board.
Okay. Okay. I'm actually not exactly sure about that, but if that software has the ability to see it, then you can see. But whatever STM softwares are available, there you have to connect the actual hardware, and without that hardware, you cannot see. So this is constraint in STM, but Texas, I'm not exactly sure. You may ask sir in the upcoming live session. I'm not sure about the Texas software.
Okay, sir. Thank you.
So we are toggling this LED2, right? So now this LED2, I have to connect, use it as a general purpose output. So that is my intention. So now if I quickly go back to the softwares for the documentation. So this is that STM user document. So here I'll go to 26 LED 2. So in that LED2, where I'm accessing this LED2, which is LD2. So LD2, it is connected to output PFI. So I have to access this PFI and I have to initialize it as GPIO file. So from the datasheet, it is there. So now I have to configure PFI to GPIO output. So after clicking that, this thing came up. Now I have to click on see this system core analog ADCs, DACs. You can configure them, timers. So first I'm clicking on GPIO. And GPIO, what I have to do, PFI to GPIO out. So I'll go to PFI. Where is my PFI? So this is my PFI. So PFI configure to GPIO output. So I have to configure to GPIO output. So as soon as I click, it is showing in green color, and configure system debug to serial bed. So this, as I have said, that it has debugger option. Either you can leave it on disable or you can keep it on serial bed. So it is just the debugger option. So you can leave it on like disable, or you can use whatever Sar has mentioned in the videos. Now we have to configure this GPIO. Again, I'm going to, again, this is, you don't have to learn. I'm just showing what can also be done, which is already shown. So output level high, and speed also we can design high or very high accordingly. And so this is the method that I have put. So you can just follow, and then clock configuration. So these are all pin configurations. So now my pin configuration is done. So now I can see whatever I have configured accordingly, it will show green color. So these are for the debug, and this is the LED I'm accessing as general purpose. So this is the pin configuration. Now I can go to the clock configuration. So this is the system clock that is the output, final output. Say I want 170 megahertz, then this can be selected. Again, you need not have to understand why this has been done. This is mentioned in the datasheet. If you select PLL clock, select PLL clock, and this should be by 4, and this should be into 85. When you select this, it becomes 170 megahertz. So it is the maximum frequency. Again, all these calculations are mentioned in the datasheet, but we are not going in detail. So after this, we can name it in the project manager. What is the name? Say we want LED1, and then we have to project location where you want to save. Say I want to save in my this file. I'll copy paste it, open, and it is saving there. And then after all this initialization, I'll click generate code. So I'll click generate code. Now it will automatically open IAR web bench. So let it open. So when it opens IAR web page, now what happens is previously all these are initialized, right? So all these drivers, everything, it has initialized. all the HAL initialization, everything. But now it is not initialized. So we have to write the code all by ourselves. So how we are going to write, let it open. So now it says either I can open folder or project. So let us open folder and see. So this is the folder. Inside the code LED1 I have written EWOM. So EWOM, I'll open project. So let it open. So inside this application, EWOM, user, code, I have main.c. So it initialized GPIO HAL initialization, but inside while there is no code because I have not written the code. So now we have to do the code from scratch. So again, if you go back here, we have to go to the driver HAL. So we need this GPIO pin. So where is the syntax? So they provide in this HAL driver HAL GPIO. Now in this GPIO, what I want GPIO toggle pin. So there is a function. So you have to click here. I'll just quickly go through it. You need not actually fully understand all these things. I'm just showing what can be done. So I'll click this. Now it gives me this function. Now I'll go back to main.c and I'll paste it and semicolon. So now I have to define this GPIO pin. So I'll go down and wherever it has initialized. So my GPIO GPIO pin 5. So from this, I'll copy paste which GPIO I have to tell this function. So I have told that it is GPIO pin 5 and it is GPIO A. So now, so let me change the color. So again, let us use some different color. So this is to for toggling. For how much time it should toggle. So this is the function HAL delay. So they have function directly for toggling. So I'll use that function HAL delay. So HAL. So it is automatically showing functions. So I'll say HAL delay and I'll mention millisecond. How many? Say 1000 millisecond, which is 1 second. Then what I have to do, project compile, project rebuild all. So I have to go to project compile and let it compile. If it has errors, then semicolon is missing. So it throw an error. So now I have to go to project and I have to compile it again. Now the build got succeeded. So now I will go to project and do rebuild all. So it will build the code. After that, I have to download and debug. So now I'll connect my microcontroller. So build is succeeded. Now I'll connect this as my microcontroller and then it is done. Now I'll run it and my code will work. So if you can see my video, so like this, okay, I think it is blur. So let me stop sharing. Stop sharing and I have to unblur my video. So again, now using this also it is running. So like the second way is a difficult way where you have to initialize what all you need and all the other things you have to do. So this is one LED example I wanted to discuss. So after this LED example, I also wanted to show another example which generates PWM signals. But let us not go into the detail of how the code has been written. More like I wanted to show what the code does. So let me save until this point and I will show another code, which is the say you can say high side low side gate driver code. So first let me close everything. Close. So now I have closed. So there is this another code which you can see my screen, right? Which is the PWM code. Hello, can you see my screen?
Yes.
Okay. I'll just quickly show. In this, I want to show what the microcontroller can do. Let us not go into the details of how this code has been written. There are several resources available online where you can learn microcontroller if you want to learn. Also, C2000 Texas Instruments, they also have so many videos available where you can learn microcontroller, and their data sheet, specific online resources you can go through and you can learn the microcontroller. But again, like different microcontroller has different syntax, different way of writing the code. So it would be very good for you if you stick on to one microcontroller rather than learning FPGA microcontroller. So whatever device you select for your application, you have to do fully that. Say if you I'm doing FPGA, if I learn Verilog and if I constantly work on Verilog, then I learn, gain more expertise in that area. If I distribute my time and my energy or multiple devices, microcontroller, FPGA, then I have to remember more things, and neither will I be gaining full expertise on FPGA, nor I'll be gaining full expertise on microcontroller. So you have to fix one device and you should dive deeper into that. So like this is the PWM configuration. So these two are the pins I have used as timer outputs. So these two give gate pulses. So I just want to show you that PA9 and PA8. So these two are the outputs. So let me go back here and let me see. So PA8 and PA9. So PA8 and PA9 are in C10, they are 21 and 23. So let me go back to the big diagram. So it has two vertical output pins, right? So one is CN10, the other one is CN7. So this is CN7, this is CN10. So as you can see, it is 1, 2. So if I have to write, so this is 1, 2. Again, this pin is 3, this pin is 4, this pin is 5, this pin is 6. So up to so on, how many pins it has? So it will be according. So let me arrange. So my pin is what? PA8 and PA9. So accordingly, I have to access that particular pin, and I should see in the oscilloscope. So let me turn on the oscilloscope. I'm turning on the oscilloscope. So leave. So this is the, like, I have configured accordingly, and now I have to go to that project. So I'll connect the pins in the document. So I have to see which pin is for what. So my pins are PA8 and PA9, right? So PA8 and PA9. There will be one diagram where it has given all the things. Not this one, not this one. So this is my CN10. So my PA8, where is PA8? So PA8 is 23rd pin and PA9 is 21 pin. And there is also another pin, which is the ground pin. So which is 20, which means 10th from the top. So I am connecting wires. I'll show you when I turn on the video. It is on the right side. So on the right side, 10th pin is ground. So I have connected ground, and below ground is 9 and then 8. So I have connected PA9, and then I have also connected PA8. So I have connected it to the oscilloscope, and now what will I do? Whatever I have opened IAR, then I'll go back here, and I'll first run it, and the build is succeeded. So it is no, I think the microcontroller is not connected, so it will throw an error. As I have mentioned, it threw an error. Let me connect the microcontroller again. Okay, so first I'll.
So this PWM code is this
Yes.
is not inbuilt, right?
No, this is
PWM
not
code.
inbuilt. This code is written, but I would like to show you the output of the code rather than how the code has been written. So I just wanted to show you one example. So now
This
the
is
code
a buck converter, right? Just synchronous.
no, like there is no buck converter. We are giving two gate pulses,
Okay.
and we are seeing like gate pulses. It can be given to
So
any converter.
no dead time is here.
Yeah, that time that that is good that you have pointed out that point. We will discuss about that time. So you can see me right now. Hello.
Yes.
Okay. So let me take
Yes.
the camera and just let me know. You can see the oscilloscope, right?
Yes.
Hello. Okay. And are the letters inverted or you can read the letters like?
Yeah, it is readable, sir. Straight
Okay,
only.
okay, okay, not inverted. So like here I have the microcontroller and yeah, so many wires. So this is the microcontroller wire and this is some other wire. And this is the microcontroller connected to USB. So this blinking means that the code is being dumped. And as I have said, I am giving 2 gate pulses and 1 ground. So this is my ground and this is 1 gate pulse and this is another gate pulse. I have connected to my probes and this is the oscilloscope. So now I will zoom out and see there are 2 gate pulses and I'd like to zoom and see. So
Sir, both probes are connected to ground, right? P8,
yes,
P8
yes.
in
So
ground and P9 in ground.
both has connected to the ground, and now I can see. Let me take this to the top. Let me bring this to the top. So there are 2 complementary signals, and if I would like to see the time period, I know this is 10 microsecond. So each grid is 10 microsecond. So the time period of the first one is from this point to this point. So if I
40.
just, so it is
15.
1, 2, 3, 4, 5. So it is 50 microsecond time period. And if I consider this to be high side, say the blue one, so its on time is 1 block of 5 such blocks. So it is 1/5. So the duty ratio is 0.2 or 20%. So say this is high side and this is low side. So both are complementary. Now the question is whether they have that time or not. So let me just zoom in. Hello, can you hear me?
Yes, sir.
Okay. Yeah, so where are we? So I wanted to see whether there is dead time or not. So I'll zoom in more. We'll keep it at the center. Then we'll be. So as you can see, there is dead time, right? So first this is break and make. So first this is broken. After some time, it is turned on, right? So this is called break and make, and you can measure the time. Say this is 20 nanosecond. So assuming that say this at this point it is turned off. So we can say 1, 2, 3, around 30 to 20, around 60 nanosecond, around that range. That time is there. So now if I zoom out, it will be same for this. So now we have seen the falling of blue and rise of yellow. Now we will see rise of blue and fall of yellow. Again, here first yellow will be brought down to 0 and then only blue will be made to 1. So let me zoom in. Already I can see that both are never 1, and now I can see that first yellow is turned off and then only blue is turned on. So, and these are this is one interesting case study of gate pulses. So this, if you want, we can give it to a gate driver which needs high side as well as low side signal. So the dead time, everything is customizable in the microcontroller. We can provide a dead time, the frequency, the time period, and all other details. So this is one
So
example.
the magnitude is
So the magnitude depends upon what voltage that we are giving to the microcontroller. Say it is 3.3 volts, then output will be from 0 to 3.3 volt. Hello. Hello.
so the waveform which you have seen is 3.3.
Yes, yes. Actually, I should have shown you. Thanks for pointing this out. Maybe I'll show you. So each grid is how much? 2 volts. So this is the say 0. From here to this grid, it is 2 volt, and from here to this grid, it is again 2 volt. So it is just more than 1.5. or you can see the peak to peak. Actually, it is not giving correct result, so never mind about that. So it is 0 and it is 3. Sorry, it is 2 volt and it is just slightly more than half. So 2 plus slightly more than 1. So it is more than 3, 3.3. Also, you can put cursors there and we can see it will be 3.3. So the FPGA input that it is taking as 3.3. So with respect to that input, it will give the voltages accordingly. Similarly, the FPGA that we have shown, it will also give 3.3. So like 3.3 is the standard voltage that is followed everywhere. So it will give 3.3. So now before we go into the upcoming topics, let me share my screen. So I'll turn off other windows so that load will reduce on my laptop. And I'll disconnect the microcontroller and I'm turning off oscilloscope as well. Let me connect back my pad. So we have discussed about STM microelectronics microcontroller, and we had spent enough time on learning about STM32 family, and then we have discussed about why we need STM32G4X family, and after that we had discussed about what are the softwares that are needed to interact with this microcontroller or dump the code into the microcontroller. And then we had first discussed about LED blinking, or you can say GPIO toggling. So in this case, we have seen two such ways. One way is an example project where everything is there. We are only just simulating and checking. The other one is starting from scratch, like Whit said. So here we have selected the pins, configured them, and written the code accordingly. So after that, we have seen some PWM waveforms where we had high side say QH as well as low side QL, and we have seen how much 50 microsecond time period. So I think it is around 20 kilohertz frequency. And duty ratio was 1/5, which is 0.2. So high side is turned on for 20% of time, and there is also dead time, finite dead time. And all these are configurable. You can change and check whether it is working or not. So these are all about the STM microcontroller. Coming to the LLC Converter Realization that has been discussed by Ranjay Malik sir, I'll quickly give a brief overview of what has been discussed and what are the advantages of microcontroller when they are using it here. So first we'll discuss about the power plant of the LLC, then the modulator, the third one is feedback management, and the fourth one is productions. Yeah, somebody saying something?
Sir, here for generating that dead time,
Yes.
you followed the same logic that we discussed, right? The time
Yes.
shifting and then undoing.
Yes, yes. Actually, you have asked one good question. Thanks for pointing it out. I'd like to add a few things. So in FPGA, code should be written for dead time, and we have to write the code accordingly, and then it will be reflected. Whereas in the case of microcontroller, you have to provide the dead time value and say other frequency accordingly. You have to choose some resistor or some variables FSW, and you have to feed it to the that code, and it will generate the dead time. It is like not to that logical level where we write the dead time. So it has that inbuilt feature where we mention the details, necessary details. And the code has so they will there are some functions which understand this, just like delay. If you consider in FPGA LED delay, I have written the delay time, everything, code, everything. Whereas here we have used a function held delay. Similarly, they have this some small modules or functions, you may say, which can be used to do specific tasks or functions. So not necessarily we have to write the code in detail. We can use some functions, but overall we have to write. And from that STM Cube MX software, you'll mention all these details. And when you generate the code, a majority of the code will be written there, and small initialization, small code like that while loop that has to be written. Is that clear?
Yes, sir. Okay.
Okay. So coming to the LLC realization. So this is the LLC converter, and you can see my screen, right? Hello.
Yes, sir.
Okay. So this is the LLC converter. We are not going into the details of working of LLC converter, all those things, but we'll just discuss. So in the power plant, there comes so many aspects like selecting these switches. So selection of MOSFETs. So it has its own challenges like RDS on, QG, all these things, and designing the resonant tank. So this is a resonant tank. What is the size of LR? What is the size of the transformer? And here either you can use diodes or you can use switches. So diodes or switches. So these are some challenges in the power stage design, but we are not discussing about LLC. Our main intention is to discuss about the use of microcontroller in such practical converter application. So LLC is basically used because it has high efficiency as well as low EMI content, and they use simple modulation schemes like PFM. And I have taken this picture from this paper. It is one of our lab's students. So you can refer to this paper if you want to know about LLC, or you can refer to other papers, but this picture has been taken from this, and here is the link. So you can access the paper as well if you are interested, but it is not necessary and not needed also. It is again up to your interest if you want to go through this paper. So coming to the modulator, as Sir has mentioned, they were using previously analog modulator, which is this L6699 controller. Now they are replacing it with this STM controller. Again, whatever we have discussed in the very beginning, it is the same thing. One is the flexibility, size, and implementing very high or complex, let's say complex algorithms easily. And here everything is hardware, so everything you have to implement in terms of hardware. All the resistor, capacitor, all those things can be directly implemented in just a microcontroller, and they will fit this. They'll use this as a control card. So they'll have this connection where they'll insert that card in the main board, and they'll dump the code, and it will run in the loop, and they don't have to use any actual hardware for controller, and they use digital controller. So these are some of the advantages when they move into the digital modulator. And some of the challenges or some of the critical cases that one should consider is the protection, which we'll discuss in the next slide. But if you see analog loop, here we have type 1, type 3 compensator. Accordingly, RC, these values will change. And here it is again well understood and popular implementation of OPAMP. But implementation is hardware dependent, because whatever RC values that we choose, everything is hardware dependent on this. Our KPK, KD values will depend, and accordingly we have to change RC, mount, again solder, desolder. All these things would be difficult because our hardware is there, the entire converter. And if you want to mount, again we have to remove the component and mount the other component, which is again a bit difficult and time taking, as well as not highly recommended to mount, demount. And also one is the space constraint. Whereas in the case of digital loop, this microcontroller, again you can implement type 1, 2, 3 compensator in that STM microcontroller. Also, it is compact and entirely code driven. You don't have to change any hardware. You just have to change the values in the code, few lines of code, and it will be accordingly changed. And it is also easy to experiment. We can give transients, pulses, everything in the controller, and we can, as I said, multiple strategies, many high complex algorithms can be implemented, and it is extremely flexible. as you have seen that LED, we have just changed one value in a function, and the time is changing. It is quite easy. And whereas if I have to implement that in a hardware, then I have to select the hardware accordingly and then implement it. If I have to change that time period again, I have to change the hardware. Whereas in the code, it is just one line of code, which will barely take 10 seconds to change. And as I've told, they'll use single card and they'll insert that card in the hardware and they'll dump the code and it will run in the closed loop. So it is very flexible, also less space, and high complex algorithms can be implemented, and very flexible, also easy to write the code. All the advantages are there. Now coming to protection. So when we are talking about high power, so protection is very crucial, as it involves so many costly components, and we do not want it to be changed completely. So we put so many protections. One is the startup sequence, how we are starting up. Say Sir has discussed 2.5 kilowatt or 6 kilowatt. So how does it start from say 0 voltage, and it will go to this high voltage? It will directly not start with that high voltage. So there will be some startup sequence that each product might be following. So how it ramps up startup sequence, and if there is any overcurrent, overload, or any short circuit, then they have to shut down so that it will not damage. Say for overcurrent, I have some 50 amperes limit. So whenever the current reaches 50 ampere limit, I can write in the code that if the current is more than this, then I will shut down the circuit. So there might be some issue. Then I have to debug and see where is that issue, and I have to resolve before it damages any other circuitry, which will be very costly, also very difficult to replace. So protection is the main important thing. Also, if the say feedback loop is open, then the microcontroller should know and should take a necessary action, and either it should stop or it should tell, or then we can use some register or flag register which says that there is some issue here and it has to be resolved. Also, if by any chance the temperature is crossing, say MOSFET temperature or GAN, the temperature is crossing, then they have to either reduce the load, or they have to make the converter shut down, so that before it damages that switch, or we should debug why this over temperature is happening before it damages the switch. Also, if there are any disconnections suddenly, then our controller should take care of all these protections, and it should ensure that none of the components get damaged. There might be a situation that it might get damaged, but we need to ensure as much as security or protection to the converter by means of code lines in the controller, so that our converter will not get damaged if there is some such issue. So, and these overcurrent, overload, short circuit, these are common in any product. So instead of directly getting damaged, they'll ensure that converter will get shut down, so that it will not damage. So some student has asked, sir, can you explain on what parameters that resonance frequency is selected? So again, we are not going into the details of LLC. Also, I'm not the person that you should be asking, because I don't have much expertise on this LLC. So LLC can be operated in different frequencies: below resonant, above resonant, or almost at resonant. So how the waveforms change. So I have slight knowledge, but not detailed knowledge. So below resonance and almost at resonance. It can also operate above resonance. So these are some of the operations at which the converter can operate, and some of these aspects, the waveforms and the modeling, has been discussed in this paper, so you can go through this paper. But I would like to tell you that it would be better if you ask sir, because I don't have that much expertise on this converter, and if you ask sir, then sir can briefly explain. And we have one live session this week. We have live session this week, Wednesday, so day after tomorrow, Wednesday. I'm not sure about the time. I think it is around 5 or 5:30 p.m. Just check, NPTEL people will inform you, so you can ask sir. Sir will briefly explain the working. Also, how to design all these things. Those are completely related to this topic, which I have not worked on, so I'm not aware of this topic that much. So you ask sir, and sir will clarify the doubts. So this is that hardware that ST people have shown in the video. So this is 2.5 kilowatt LED light electric vehicle battery charger. So it has again two parts. So if you break like this, so the left part is the PFC part, power factor correction circuit, and the right part is the LLC part. So this is giving AC to DC, and this then is changing DC to DC, and it is charging the battery. And these are different heat sinks. So all these are heat sinks. And they have designed the capacitors. These are also capacitors, transformer, inductor, and this inductor accordingly. And we are not going into the details. So these are the details of the this battery charger. So they are using mixed analog plus MCU control. So this is the microcontroller controlled converter, and this is a product that ST people have made, and they are using STM microcontroller, and the peak efficiency is 93.5%, and the power factor is greater than 0.95, and THD is less than 5%. So this is the LLC part that have been discussed in that lecture 84 and 85, where they have shown the results of inductor current at that specified frequency where it is designed for. But for details, kindly contact sir. And so this completes the LLC part, where we have just briefly discussed about the advantages of microcontroller, what all tasks can be done using the microcontroller, and the like board structure, and what protections that it should take care. All those things we had discussed. So now coming to
This is the power board, right?
yes, this is the power board. Yeah. So to this, the microcontroller will be connected.
Yes, sir. Oh, where is the connection point, sir, for all these 8
not
devices?
exactly sure about. There will be a connector. So I'm not exactly
Yes,
sure from this view.
some-
But in that video, it would be clearly visible where they have connected. But from this view, I'm not sure where they are connecting. But there will be this connector where they will connect to the microcontroller.
Okay. Okay, sir.
Okay. You refer to that video 985 or 84. So in both cases, SAR has shown from where the microcontroller is getting the details. I don't know whether it is available, but in this view, it is difficult to figure out. You just refer to that video. There, they have shown how it is connected. So we were discussing about microcontrollers today, and there are two microcontrollers. One is the ST Microelectronics microcontroller, and the other one is the Texas Instrument. So ST Microelectronics, and the other one is the Texas Instruments. So in ST Microelectronics, we have discussed about STM32 family G4X, and here we will discuss about C2000 microcontroller, which is one of the Texas Instruments microcontroller, which is quite popular. So again, we will be discussing some overview of microcontroller and what are the software tools that are necessary. We'll quickly go through because all the microcontrollers are almost similar. They are made for different applications, and they might have some additional benefits, but majority it is the same. So majority of the microcontrollers, they almost have same features. So here C2000 real-time microcontrollers, they're also made for wide range of applications, starting from energy delivery and then for digital power. So they have mentioned what all applications it is targeted for. Here, telecom, AC/DC rectifiers, DC/DC converters. So this is our area of domain, and they're also made for high voltage DC/DC onboard charging, very high power applications, as well as motor drives, traction drive, compressor, automotive. So this all comes under automotive. So automotive inside the motors, also charging electric vehicle, and then for industrial devs, for automation, robotics, and again here motor control for drones, bikes, and other pipes. So this is our area where we are discussing about the DC/DC converter. So this is the application where we are targeting, and the usage of 2000 microcontrollers, what benefits that it offers, and whether they have ADC/DAC similar to STM32 or we'll see the overview. So the overview of the C2000, again, all these slides are taken from the Texas Instruments people who have provided, and these are again discussed in detail in the lectures. I'm just giving a brief summary. So they also have very high accurate sensing, and they also have 12-bit or 16-bit ADCs up to 24 channels. So depending upon that, you have to configure the channels and then use it. And they also have comparators with built-in DACs. So they also have ADCs, DACs, comparators, because it is specifically made for this application. So whatever hardware that is needed, it will be inbuilt in that. And they also have very high resolution PWMs. So, and they can give up to 32 output PWM. So you can configure that general purpose input output pins and then use it. And they also have buffered output DACs. And they also have different reference designs. So you can get it from their website, and you can also get so many example projects, and you can access them and test whether it is working or not. So you can actually sense signals, also control them by writing the control. And also it has some functional safety things. Again, everything will be similar to what we have already discussed there. And it also has so many integrated communication, CAN, UART, SPI, to CPF, bus, USB, different Ethernet also it has. So depending upon your requirements, you can configure any of this communication, and you can operate. And also they are using different core, multi-core architecture for that to achieve high performance using this microcontroller. And it can do up to 925 MIPS. So this is million instructions per second. So MIPS means million. Right. So they can do up to 925 million instructions per second. Again, you have to look at the datasheet, what is the clock frequency that they are using, and what is the resolution that this microcontroller is offering. All these details you can find in their datasheet. So similar to what ST has different wide range of microcontrollers that are available. Here also they have three set of family, you can say. So one is the entry level performance. So here they offer 150 MIPS, so which is somewhat, you can say, low performance. And this one is the mid performance. So here they can offer up to 150 to 600 billion instructions per second. And the third one is the high performance, which is above, I think I should look at this color. So which is about 600 million instructions per second. And as you can see, these are the memory, 1 MB, 1.5 MB, and it has 925 million instructions per second. So depending upon their applications, if you need high performance, then you have to go for high performance. Accordingly, the cost will vary and the performance will of course vary. And I think this is the new one, where they are going 240 MIPS and 384 KB. That is the memory. So depending upon again the application, we have to select that microcontroller. There are wide range of microcontrollers available both in ST as well as in Texas, depending upon our cost, size, flexibility, ease of usage. All these things we can consider, or we have to select any one of that microcontroller, and accordingly we have to design our digital controller. So like this is the same. So here they have categorized based on MIPS, and here they have categorized based on flash size and performance. So
What is this flash memory, sir?
so the amount of flash memory that you can access. So each microcontroller has some memory where you can store some data values. Depending upon how much memory it has, it is proportional to the size of the data that you can store. We will not be using for our applications, but for different applications, they might have to store data. So depending upon their applications, they might have to store data. But in our applications, we are not storing any data. So ours is like getting the information from the V0, and we are generating the gate pulse, but we are not storing any data. But there might be some applications where they have to store data, and they might be needing. So accordingly, if your application requires or demands high flash size, then you'll have to choose a microcontroller which can offer that much size. and also high performance. If we are operating, say, high frequency DC-DC converter, high frequency, so the frequency itself is high, so the time period, say it is in a few milliseconds. So our microcontroller has to generate the reference within a few microseconds, which means it has to compute all these instructions at very high speed. So accordingly, we have to choose. If we choose very low like performance microcontroller, then it itself will take more number of cycles than the converter itself. So it is not compatible for that application. So depending upon the frequency at which you want to operate the converter, or depending upon what size, flash size that is required for whatever you are designing, you have to select that particular microcontroller and then implement your control technique in that controller. So these are all very high speed as well as high MB 800 bits and 1 MB 800 bits, 512 MB. So this is this is performance, and this is flash size. So proportionally, the cost might also increase. So the cost will also increase as performance increases, also flash size increases. So again, yeah.
Sir, suppose we are having some topology, buck
Yes.
booster, buck booster now.
Yes.
Sir, based on which we need to select a particular microcontroller
Yeah.
for our
So,
application.
yeah. So like say you are operating in say mixed current mode control at some frequency, say 500 kilohertz. So your time period is 2 microseconds. Now we'll choose a device which will be able to generate that reference within this 2 microseconds, because you have to change the reference every cycle. So how many number of lines you will be needing, and whether the controller will be able to provide that much high performance or not, and whether you need ADCs, DACs, comparators, and what is the resolution. Say you are operating in voltage mode control, what is the resolution that that particular controller is offering. Say if the resolution is low resolution, then the counter step size will be more, and we don't have high resolution. So we have to again see, again it depends upon the clock frequency that that particular microcontroller is providing. So depending upon all these things, you choose. So say this microcontroller is sufficient for me, for example, then I can use this, because they are high performance, and they have more flashes than this. Again, then it depends upon the user whether that application can afford this much cost microcontroller or not. Then we'll go with the low cost microcontroller and we'll use this. So that application decides. Is that clear? Hello.
Yes. Sir, is there any way by which if we give our specifications of our converter, will they suggest any
No,
portal in
not
STM or
any
here available?
like such a website as such, but again you should see like your application is digital power, right? So this itself will narrow down the microcontroller. So you can see, go to the TA website and see what all microcontrollers they have made specifically for DC-DC converters. So it will give the set of family, similarly to STM, where it has 4 such families, and we have narrowed down it to the mixed like the microcontroller optimized for mixed signal application. Similarly, you have to see which family of this microcontroller is suitable for DC-DC converters. So in digital power, they have different applications. So you should see which microcontroller is optimized for DC-DC converters. In that DC-DC converter, you might be getting 3-4 families. So in that 3-4 families, you should compare which family offers what benefits. What is the clock frequency? How many ADCs are available? What is the resolution? All these things, and then you should decide based on the cost and performance, So everything, it is a trade-off between cost versus performance, right? So if you want high performance, the cost will increase. If you want less cost, the performance decreases. Then accordingly, satisfying this trade-off, we should go to that particular microcontroller which offers decent performance and decent cost. So your application narrow downs the family of the microcontrollers that you can use. Is that clear?
Yes.
Okay.
Yes.
So again, these are different, like similar to what we had discussed in STM32, why we had gone for that STM32G4 series, because it is optimized for mixed signal application. Similarly, why C2000, because it has accurate voltage sensing and precise ADCs, and it has built-in DACs, built-in comparators, and PWMs, very high resolution PWM, and they have different benefits as well, as they are saying EPWM mode enabling peak current mode control, also RAM compensation. So each microcontroller has a different set of benefits. So you should see which one is more suitable to the application that you are working on, and based on that, you will select that microcontroller. There may be n number of microcontrollers that are fitting into the application that you are working on. Then comes the cost versus performance. So you can either settle with lesser cost, decent performance, or you can settle with high performance, high cost. Again, it is based on the user as well as the cost that that particular product can afford. Again, they have different voltage loop, current loop, bandwidth, optimized cores, and this floating processing unit, whether you will be using floating point or fixed point, it depends upon that. And then they have this, I think, trigonometric math unit. So TMU is the trigonometric math unit, whether you will be using trigonometric things or not. If you're not, then you will not be using. But say your application needs trigonometric computations, say sine, cosine, tan, then you will choose a microcontroller which has been optimized for the trigonometric math. Say, when I say optimized, it means it will compute all these things in lesser number of cycles. So optimized in the sense hardware is also optimized, and also the time is also optimized. So optimized in the sense less number of instruction cycles. So within less number of instruction, it will be able to detect that sine x value or cosine x value or whatever that you have to see what it can do. And it will have additional flexibility, most advanced high frequency switching techniques. So it is basically designed for high frequency switch mode power converters and increased efficiency and power density. So all these things you have to check which one is offering what and which will most suitably fit into our application. And here they have 150 picosecond resolution. Also at a time we can do 4 different compare events, and many ADCs are there. So if you need more ADCs, then you have to see whether that many ADCs are available or not. Then we have to see STM has 5 ADCs, whether this has more ADCs, less ADCs. Depending upon the application, we choose the microcontroller. And they also have different ecosystem. So, sorry. So we have one question here. Sir, can you explain EPWM? So EPWM, they are saying enhanced PWM. So again, you have to see what is the difference between EPWM and PWM. What do they mean by enhanced PWM? So whether they mean high resolution, or what is the advantage, that again you have to go into the datasheet or a Texas Instrument website, and you have to see, because it is specific to that EPWM block. So they are saying tight integration to EPWM block enabling peak current mode control. So which might be the case, I'm thinking possibly it could be, because we need very high resolution, right? So I'm thinking EPWM could be very high resolution PWM. So the error margin, so the reset, this error margin could be minimized when you use that particular enhanced PWM, which is again optimized for one particular application peak current. But again, the details you have to go through their datasheet and see what exactly it is making, what additional benefits it is generating, because these are very application specific and very specific to that particular controller. You have to again go through that datasheet and then comment. We cannot actually comment as of now, but we should check the datasheet and. So again, it has different ecosystem, and they have different products. So C2000, in the C2000, they have launch pads, they have control codes. So this will fit into that board as we are discussing the single control card for the entire plant, and they have different application kits. So they have made for particular application. As you can see inductors here. So they have made that kit for that particular application. So if needed, you can directly buy it and then test it. So they have some debug probes as well as programmers, and also different softwares that they can use. C2000 ware or digital power or motor control. And these are some reference designs that are already available open, and these are the links that they have provided. So for different application, for different topologies, say PSFB and two-phase interleaved LLC, two-phase interleaved boost converter with isolation, phase shifted full bridge. So PSFB is phase shifted full bridge converter. So you can click on this link and see what reference design they are offering, whether you can refer to that or whether it will be beneficial, what type of control techniques they are using, all these things you can see. There is less than a minute, so if this meeting ends, kindly join. So maybe I can show this reference design. So let me just click on one reference design and see what details they're mentioning. So this has taken me to their website. I think the meeting will end. So quickly join, then we can discuss. You can hear me, right? Hello. Okay.
Yes, sir.
Okay. The meeting might end, so let it end. When we come back, we can discuss. So it has overview where they'll describe all the features that. So it has taken me to this website, whatever that particular board that I have selected. So it is 400 volt DC input, and it will regulate 12 volt DC output. And it is digital peak current mode control, phase shifted full bridge DC-DC converter. So if I want to go to the documentation, I'll click on technical documentation, which will take me to this design guide, and where I can find details regarding this. So this is the board, and as you can see, this is the control card. So they are fitting this control card, and this has all the controller microcontroller details. So it takes information using that interconnection between this and the control digital peak current mode control, whatever they have mentioned, it will happen, and again it will send signals back here. So this is the topology that they are using. So we can find details that overall diagram, and this is the phase shifted full bridge circuit and the waveforms, and how it is happening, how that controller is working. So they are discussing about the implementation, and all the things that they have implemented, they'll give a brief discussion. So they are explaining the board. So what it has. So this is the canvas and USB tag. I think this is the controller card. And this is the low voltage side, high voltage side, and you can go through the data sheet. Similarly, these are for one particular application, and you can go to different applications. So here they're showing how to start the project and then dump the code. So they'll discuss all the necessary details. So we can particularly open it, and they're showing some results, and accordingly they are operating. So this is the software frequency response analyzer SFRA, which is also Texas Instruments developed software online tool. So these are all the things that are available freely online, and these are done by the Texas Instruments. So you can check any reference design, maybe DC-DC converter. You can see whether boost converter reference design is available or buck converter reference design is available. And these are some software products that Texas Instrument is offering. One is C2000 ware, which you can use for C2000 microcontroller, and this motor control SDK for that particular three-phase. It is targeted for three-phase motor control application, and digital power SDK. So this is for the digital power application, and what are the targeted softwares, sorry, targeted applications that it has, and this is also built on top of C2000 ware. So this is the basic software, and these are all built on top of C2000 ware. This is also built on top of C2000 ware, and then this is safety SW. So what it offers, all these things are available in the link that they have provided, but we are not actually learning what the details that this software is providing. We are just giving you introduction of what all softwares are available for what all different applications. But it again depends upon, depending upon your interest, you are free to explore and learn about all these softwares. But it is not mandatory for you to learn all the software working for the final exam. This is only for you to understand how this thing works, what are all the softwares, and what is the user interface, how we can use it. And we'll not ask you to implement any of that and submit, and we will neither ask you how to implement it in software, but a basic understanding of what is being done. That is the most important thing, and how to select the controllers and what all controllers are available, and how to select controllers for different applications. This is the important thing that you should keep in mind. So, and TA also has this PowerSuite digital power software tools. So they have also mentioned how to do this. So first they have this TI source code to create this customized version in solution adapter. So you can connect circuits are available. So you can fit L and C values, and they have this compensator designer. So let me write. So they have all these tools are already there, and they have made. So there is this tool called compensation designer. So using which you can design it using the board uploads, and then you can go to that project in Composer Studio, and then you can fit this in the Composer Studio, and then using this SFRA, which is the software frequency response analyzer, it will give both closed loop as well as open loop transfer functions, or you can say loop transfer function, gain as well as phase. So from this we can get gain crossover frequency or bandwidth and phase margin. So we'll see whether it is fitting our application or not. If it is not, then again we'll go back to compensator design, and we can this will happen in a loop. So this is TA software, which is very useful to design all these things, and they have the simulation, I think, inside it. So you can access it, and you can design your compensator, and then you can write the code and implement it in the C2000 microcontroller. So similar to what ST people are doing, Texas people are also working on the same thing. So this is GAN based. So they have used GAN, continuous conduction mode. This is continuous conduction mode. Totem pole bidirectional PFC. So they have this input over here, and this is the input AC filter. This in rush current and relay circuit. So this is again protection. If there is any high current, then it will be triggered and it will turn on the working of the converter. And see, this is the control card we are talking about. So whatever card they are using, it will take the data from the power board, and all the computation will happen digital controller, and it will be sending back necessary signal. If you see, it is fit vertically, so the space that it is taking will be very less. As you can see, if you take the cross-sectional area, which is very less, and all the complex algorithms can be done inside this, and it will be very cost efficient, also very high density. And they have this power supply input and other frequency switches and diode bridges here. So again, this controller card can implement advanced control techniques like phase shading, adaptive deadtime, and AC drop. So adaptive deadtime is like they change the deadtime, they vary the deadtime according to the load current or other operating conditions, so that it will be efficient in terms of efficiency. So maybe some particular operation, that time should be more or that time should be less. So they will feed all the codes inside this controller code. So accordingly, the data time will be varied, and which will be resulting in high efficiency. And they have given formula for Deadtime also. So based on that formula, they will write the code accordingly, and it will generate the Deadtime, and it will be implemented in the C2000. So just to summarize, today we have discussed about microcontrollers. So we have discussed about two microcontrollers. One is the STM32G4X, and the other one is C2000. So in STM32G4X, we have shown one GPIO toggling. Also, we have seen PWM function. Here we have not seen any, but it will be similar to whatever we had done here. So they might be using some different syntax, some different instruction. Syntax will be different, but it will be all the microcontrollers are almost similar. And here we have discussed about LLC converter, whatever they have made, ST people may have made. And in this case, we have discussed about a PFC converter. So whatever they have made and how beneficial it is to use microcontroller for implementing complex algorithms or reducing space or increasing the power density of the converter. All these things we have discussed. So as there is no as such problems in this week, but we can have like two problems so that we can check how much we have understood about the microcontrollers. So this is one first question. So the question is that we have a microcontroller, and it is being used to operate buck converter under voltage mode control. It's a digital voltage mode control. And the microcontroller is using a 170 megahertz clock. And so this is the first part is ADC, and the other part is computation and generation of PWM. So what the question says is ADC takes 15 instructions to generate ADC. So by the time it takes sample and by the time it gives an out, it takes 15 instructions to do this conversion. And the computation and the generation of PWM will take 25 instructions. So the question says, what will be the time to execute each block in feedback, and what is the time taken? So if you consider this as one block and this is the other block, what is the time taken by block 1, block 2, as well as total time taken by block 1 and block 2. So let me start with block 1. So each instruction will take one switching clock cycle, because each instruction will take one clock cycle. So if we consider in such way, we have T clock is 1 by 170 megahertz or 1 by 170 microsecond or 1000 by 170 nanosecond. So 100 by 17, it is around 5 point something nanosecond. Now block 1 will take how much time? T clock. Will take 15 into T clock, isn't it? Hello. Hello.
Yes, sir.
Yes,
Sir,
yes.
And how much time block 2 takes? Block 2 time means the computation and generation of PWM.
25 into T clock.
So it will take 25 into T clock, because each instruction line will take one clock cycle. So what is the total time now? For computation of both.
15 into T clock.
So it is 15 plus 25, which is 40 into T clock. So we have to calculate, this is so 40 into 100 by 17 nanoseconds. T clock. That much time it will take, and it should be again lesser than our time period, because the PWM signal should be generated within that switching clock cycle, right? So it should be faster. So accordingly, we have to select the microcontroller as we have discussed before. So now
Sir, what is this PWM, sir? Sir, please repeat that one.
So like this is this
How you are comparing?
voltage mode control, the architecture. and this is being written in code and it is being implemented in MCU. So if I consider it as two blocks, say the first block is ADC block and the second block is computation and generation of PWM block. The question says this ADC block will take 15 instructions to generate the digital equivalent of output voltage. So it will take 15 instructions to come for compute. And after getting this ADC, this will take 25 instructions to reflect or to convert this equivalent digital output voltage into PWM and PWM. So this is my entire control. Now the question is, what time does this block take to execute and out, and what time does this block take to execute or give PWM and PWM? As we know, each instruction line will take one clock cycle. So from the clock information, I got the each like instruction time, which is T clock. And then based on the information that they have given, I'll know that ADC computation will take 15 into T clock because 15 instructions, and this will take 25 into T clock. So the total time is this plus this because they are happening serially. Until this happens, this will not start. So this plus this is 40 T clock, and I know that that time from which V0 sample is being taken and the PWM generation, it should be faster and it should happen within one switching cycle, right? So if switching frequency is FSW, time period is T switching TSW. So I'm saying this total time should be less than TSW because our controller should be faster than switching clock so that it can compute the gate pulses within a single cycle. Because if it takes more than single cycle, so before the next on-time pulse starts, the controller is not giving the information. So then you cannot use that. So the controller should be fast enough and it should give that gate pulse. Is
Yeah,
that
this
clear?
entire thing is for
Yeah. Is
Sir?
this entire thing is for?
this entire thing is for 40 cycles it takes for a sample to have its effect on the PWM.
PWM, yeah. So the by that moment V0 sample has started to the moment PWM has generated, it takes 40 clock cycles for the entire computation for my controller.
So the time of the 40 clock cycles should be less than the TSW.
TSW, because this is my inductor current and this is my V0. So using this V0 sample, say at this point, I have to, once I get delay, I have to give the gate pulse here, right? So whatever my controller does, it has this TSW time to give me this gate pulse information at this moment, right? So if it takes more time, then who will give me this gate pulse information? So whatever computation that controller does, it should be less than TSW, which means it takes less than a switching clock cycle to generate the gate pulse for the upcoming cycle, something like that. This is clear?
Or
Sir,
if
but
like this computation is greater than the TSW, then the pulse given will be like it will be there, right?
See, like I am giving.
Sir, exactly I want to know what's the issue if the time is less greater than TSW.
Okay. So say this is the inductor current, and this is the output voltage. I need the gate pulse information, or you can say, let us consider voltage mode controller. So voltage mode control, I am comparing with the, this is one cycle here. So it is being compared with the reference, right? So I'll use this VCon, and it is being changed. And we had discussed VCon has one switching cycle delay. So that VCon say I am sampling here, this will be reflected in this beacon, right? And similarly, I will sample here, and this will be reflected in this beacon. This will be reflected in this beacon. Now, whatever voltage that it has taken, it should be available for me in this switching cycle, right? If this is not available here, now we have 1 cycle delay. If this is available here, then we'll have 2 cycle delay, which we do not want. We are fixing 1 cycle delay for the reason we had discussed in the earlier weeks. So whatever sample that I had here, it should be available to me before this instant. So whatever I will implement, whichever microcontroller I'll use or FPGA I'll use, it should be capable enough to give me this VCon at this instant, provided I am giving it the voltage sample at this point. Understood? Else my delay will increase, right? So if this is giving me here, then I'll have 2 cycle delay instead of 1 cycle delay.
Sir, if that is the case, that desired value, what we are wanting, what we are desired, it will take more time, right?
Yes, yes. So then it will have
For
stability
control.
issues. Yes, yes.
Okay. Okay, sir. Okay.
Or you can also think in this way. Say I am taking the sample here to calculate VCon, which is the output. So this is my V reference. This is my V naught. This is my GC of S, and this is my VCon. This is my V error. And this V naught has ADC here. Input is V naught. See, my ADC has to be much faster, right? See, I have taken sample here. If my ADC itself will give the digital equivalent signal at this instant, then by the time VCon is generated, it will be even more delayed. So my ADC has to say take this much time for computation TADC, and after this instant, this will be generated into VCon. So then my PID controller time will come. So my ADC has to be faster. So my ADC has to compute it in less than a cycle, a fraction of TSW, and then after this signal, after this V naught N is available, now this V naught N is converted into VCon N, and this entire time should be less than like say TSW or less than TSW. So if my entire time is less than TSW, my ADC computation time TADC should be lesser than TSW, right? So ADC has to be faster. So accordingly, we are saying, because I want the reflected VCon to be in the next cycle, so I have 1 cycle time for all my computation. So whatever controller, digital controller, say FPGA or whatever I am using, it should be capable of doing.
Sir,
Yeah.
sir, in this case, if we go for the current mode control and another mix-up, sir, in that, so there will be a limitation in frequency that we can operate there, right? Because this number of this delay will increase if you go for sequence.
Yes, yes. As not as such, because in the case of this also same. Say this is V naught, and this sample will be reflected as reference here. So this sample will be reflected as reference here. So this sample, V naught sample, has to be converted into this I reference of N within a switching cycle. And whatever sample that has been considered here, it will be reflected in V reference of N within a switching cycle. So before that next switching cycle start, my controller has to already compute the value of this I reference of N and should keep it ready so that I can compare it with my inductor current. Understood?
So there will not be much variation in
Yes,
the frequency that we can operate.
So now if I can operate at 10 megahertz or 20 megahertz, that you should see whether your controller will be capable enough of operating at that much high frequency. So Yeah, that is the thing. As far as it is less than 1 megahertz, not much problem, because like whatever controllers that we are using, they are much faster than this, and they'll be able to do within fraction of microseconds. Is that clear?
Yes, sir.
Okay. So this is problem one. So in problem two, we have some statements about digital control, and I'm asking which of them are true. So whether digital controller, maybe I should use digital controller or microcontroller. It is compact and entirely code driven. Is this true?
Yes.
Maybe
Yes. Yes, sir.
I'm sure about the compactness, but not like whether it is entirely code driven or not.
why it is not code driven? Say like digital control, by here I mean microcontroller, whatever we have discussed today. Is it not code driven?
Yes, it is code driven.
Yes. So whatever you are writing the code, it
Compact
is
also.
compiled into the controller. So you are basically writing the code, nothing about the hardware you are doing, right? Only you are doing the software code simulation and dumping it into the already available microcontroller. You are neither changing any hardware nor adding any hardware. So we are only writing the code on already available hardware. So it is true. So this is true. And is it having high power density? You mean, is it leading to high power density?
Like, what is its meaning, sir?
So it means whether digital control implementation using microcontroller, whether it has higher density compared to analog control. Higher density in the sense size, whether size is less or not.
Compared to analog control, here
yes.
the size is less.
Yes. So compared to analog control, the size is less. So this is also true. And it is difficult to experiment.
No.
So this is false, because it is easy and we can just make some small modifications in the code and we can implement it. And high functionalities and can handle complex algorithms.
True.
And multiple strategies can be implemented.
Yes. True.
And it is not flexible.
False.
Because it is highly flexible and we are flexible to change any values at any time and implement it quickly. Multiple control cards are needed to control.
No.
False. So like this slide, we can also say or summarize. So it has high density. So the like conclusion of microcontrollers, it has high density, or you can say small size or fixed size, compared to whatever we are saying. It is compared to analog control, and it is compact and completely code driven, and it is easy to do experiments, and it has functionality to implement complex algorithms easily. So whatever we are saying, we are saying from our side. Yes.
Sir, for implementing certain complex control algorithm, we need the docking board, right? Docking board and docking station.
Like say whatever controller I have shown today, that controller with the installed softwares should be sufficient.
So I'm saying this last one should be true, right? That multiple control cards are
No,
needed to
only
control.
single control card is needed, right? So whatever
Yeah,
they are doing,
whatever our application, it is okay.
single control card in any application. See, this is a very high power application where they are doing
Charger.
So this is a 2.5 kilowatt EV charger, and they need one controller only. They will not need many controllers, because this controller itself has capability of doing all the things by itself. It has many ADCs, DACs, comparators, everything. So they'll need only single control card for all the things that it can do. So only one control card should be sufficient for any application. Actually, it is more than enough. So we don't need multiple control cards. We only need single control card, and it is more than enough, or it should be sufficient.
Okay.
So with that, we can conclude our session. Just to summarize, we have
Sir, I
discussed
have
about,
a doubt.
yeah.
Sir, in analog control, like there is a, in the slide you have mentioned, for something there is a reference value, sir.
Yes, so that
Other
reference
than the
is,
feedback, how it is set in analog?
so this is that reference. Okay. I'll use this reference. So there are something called
Like from fixed
linear dropout.
supply.
Yes. So linear dropout regulators, or you can say voltage regulators. They are also called LDOs. So what this LDOs does, or LDOs do, is that I'm representing in terms of an IC. So it takes fixed supply, 5-volt ground, and it generates a one standard LDO is 3.3 volt. Now what I'll do, this 3.3 volt, I'll give it to a resistor divider, and I'll generate whatever voltage I need. Say I need 1.5 volt. I'll generate 1.5 volt. Now who will decide these resistors? It is my choice to design these resistors. R2 by R1 plus R2 is 1.5 by 3.3. So from this I'll get the, this is one way of designing. There can be multiple ways, but this is a most standard way where people use this everywhere. So this is one standard way. And so now this will give me R1 comma R2 values. So now the question is, say I don't want 1.5 volt. I want 2 volt. Now what we have to do, we have to change this R1 and R2 by calculating this equation, which I don't want. Whereas in the case of code, I can just change the reference value in that code line and it will be easy. So here you have to change the R1, R2 resistors and mount them, right? Whereas in the case of digital, it is just a line code line. Is that clear? Hello.
There it is shown inside the block diagram. Like inside the block diagram also the same concept
They are
is used,
generating.
right?
So like say that there is that big IC.
Sir, in that, sir, if possible, could you please move to the 1 to 5 slides, I guess.
Yeah. So this is what we are talking about. So
Sir,
this VCC, every IC needs a VCC. So this could be 5 volt or 12 volt. Based on this 5 volt, 12 volt, it internally generates this reference by means of LDOs or whatever hardware they're using, and it is fixed. And there might be a provision for us to change by externally connecting a resistor, but again you have to mount and change the resistors accordingly, which is a bit tedious job to do because we have to change that resistors accordingly. But that is actually done inside. But if you want to do it by yourself, then this is one way where you can use LDOs, and you have to connect a resistor divider to bring that voltage down to whatever voltage you need. If you see SARS code, SAR has used NREF, which is a line of just a single line, right? So if SAR wants to, if you see in SAR's reference transient, whatever reference transient SAR is using, SAR has changed NREF to NREF plus delta NREF, right? So SAR has done nothing in the hardware. SAR has done everything in the code, and which would be much easier to change this R1 and R2, right? It is just the flexibility and ease of implementing whatever we want to do. Banerjee, is that clear?
it's clear.
Okay. So just to summarize, today we have discussed about microcontrollers, the ST Microelectronics microcontroller, STM G4X microcontroller, and the C2000 microcontroller of Texas Instruments. And in STM, we have seen some basic code implementation of LED as well as PWM signal. And in LED, we have seen two different ways: one directly accessing the example project, and the other one is writing the code from scratch. And for PWM, we have not seen the code implementation. Rather, we have seen what is the output and what flexibilities it has, like changing the dead time, duty ratio, frequency, everything. And coming to C2000, before C2000, we also discussed the LLC Converter, a practical application of ST Microelectronics product where they're using STM microcontroller. And then coming to C2000, we have discussed the offer benefits that C2000 microcontroller offers and what all things that it come up with, like ADC stacks, EPWM, other benefits, and like trigonometric math unit, TMUs, FPUs. And then we have seen the product that they're using C2000 microcontroller, like PFC, and we have discussed about different reference designs that they are offering. And in the end, we have discussed a few problems to summarize what we have discussed and assess our understanding. If you have any doubts, you can ask, else we can conclude this session here. Do you have any doubts?
Thank you, sir.
Okay. And this week, Wednesday, we have one live session with sir. Please do join. And if you have any doubts, you can ask sir, and sir will be discussing many detailed aspects of all the things that we have covered in LLC PFC scope. Please
Okay.
join and ask. Have a great discussion. with sir.
Okay, okay.
Thank you.
Good night, sir. Thank you.
Good night. Thank you.